Hi, this is Paul from Tech. In this video, we are going to deal with the Newton's method, which we can use to approximate the root of an equation. Let's see the outline. First, I will introduce Newton's method. Then, we will practice only one question together about how to use Newton's method. Let's see the material. Here is Newton's method. Of course, the method was proposed originally by Isaac Newton. So first, what the question do we have? If we have equation fx equals 0, if the equation is too hard to solve explicitly, so what do? We have to do approximation, right? And the Newton's method is iterative algorithm to do approximation. Let me see, the formula is here. Xn plus 1 equals xn minus f at xn over f prime at xn. Okay, this is the iterative algorithm. What does this mean? Let me show here. Suppose we have one point, okay, one number, which is x0. We call the initial value. Okay, let me show. X0 is we call the initial value. Okay, so this is initial, which means what? The algorithm starts from this initial point, initial number, and then we plug into this formula. This time n equals 0, right? Therefore, we can get what? We can get x1 equals x0 minus f at x0 over f prime at x0. See, if we know x0, plug into this formula, what do we get? We will get another x. We call it x1. This is the second. This is the first step, which means what? Start from the initial x0, now we have x1. Okay, this we call the iterative. The same, okay, start from x1, we plug x1 into this formula, which means let n be 1. This time we can iteratively find x2, the next number. Okay, the same situation. If we plug x2 into this formula, what do we get? We will get x3. And then we will, if we put the x3 into the right side, now we will get x4. Imagine. So now what do we have? We have a sequence. Okay, if we go into chapter 11, okay, so we will discuss what is the sequence mean. Okay, just like this. If we have x0, x1, x2, x3, n goes up into infinity. This is an infinite sequence, and the limit exists. Okay, can you see? This theorem gives us the limit exists and exactly equals 1 equals c, and then c should be the root of this equation. Okay, in theory, c is the root of this equation, and in practically, of course, we cannot exactly find the c, but what do? We can take n is large enough, so xn will approximate to c. That's the strategy. Okay, let me highlight this formula. This is the only formula. Look, it's very strange, right? So let me show a leader. So why? The limit c is the root of the equation. Super easy to find. Can you see? This limit is c, right? Project c. This limit is, of course, is project c. So what do we get? In minus c both sides, we will get this top should be project 0. And this numerator project 0. What is this numerator? This numerator, of course, is f at c, right? If the function is continuous, of course, the function should be continuous. So equals 0. Have you get it? So f at c equals 0. Okay, and then now what do we need to do? We need to understand what does this formula mean. Now it does not make sense to us, right? Let's look at a graph, so we will have to understand what does this formula mean. Can you see? Okay, so suppose we have a function is here. This function is y equals f. Okay, now let's start. If we have a function, can we look at where is the solution? C is at here, right? Okay, can you see C is at here? Or let me put a little bit. If this is the function, the green one at the function, like y equals fx. Where is the root of the function? We know is here. Can you see? Okay, this point is what? This point is C. That's the one we need to find. Okay, and how do you find this root of C? We do this. Can we see? Give a point x0, which is the initial. Okay, which means whatever we set up x0 here. What is this point? Of course, this point is x0, f at x0, right? And then we draw a tangent line. What do we find? And this x-intercept of the tangent line is just the x1. Okay, we just see the very strange formula, right? Okay, exactly what that is iterative, which means here. Okay, we find that the tangent line, and then we find that the solution, or the zero, or the root of the tangent line, which is x1, do the same. Okay, if we draw a vertical line, and then we have x1, f at x1, this point, the same, draw a tangent line, and then we have another root. Can you see? Now we have x0, now x1, x2, x3, dot, dot, dot. This is a sequence, right? Can you see? Well, look at this graph. Of course, this sequence approaches C. And therefore, if we put n is large enough, so we can do the approximation. Of course, why this x1 is just the formula. Okay, so let me going to do a little calculation. We are going to find this. Okay, so all we need is just do calculation. See if the formula is just the formula we just see. Okay, I put here. This is the tangent line, right? This is the tangent line. So first we need to find the tangent line, which is y minus y0, which is f at x0 equals. The derivative is just the slope, right? So this is the slope. And the x minus x0. See, and this is the tangent line. And we need to find out what? We need to find this x1. Okay, so x1, we need to set up y is 0, right? And this x should be x1. And let me put in. So this should be how many? Let me write it in this way. This y, this time should be 0, right? Okay, so minus f x0 equals f prime, and this x should be what we need. We need the x1, right? Okay, and then minus x0. Okay, solve this equation to find that what is x1. Easy to solve. Divided by f prime, so we have this negative f at x0 over f prime at x0 equals x1 minus x0. We need the x1, so plus x0 both sides. Can you see what do we get? We will get this x1 equals, right, x0 minus f at x0 over f prime at x0. If we highlight it, this is the iterative formula. Okay, have you see? Is it the same? Yeah, of course. Okay, if I give you x0, we plug this formula and we'll find x1. The same, if we plug x1 into this 0, we find x2. Therefore, x2 equals x1 minus f at x1, right? And divided by f prime at x1. The same for x2, x3, x4 continues. Okay, this is the formula. Super easy to get. Okay, and you know this method. Okay, it's a very genius method, right? See, we just find the root of the tangent line, and the root of the tangent line approach, all these approach we call the converges, okay? Converges to the root of C. Therefore, we can do approximation easily. Now we have these two comments for you. The first, how to choose the initial value? Okay, so someone will choose the initial value at here, or someone will choose the initial value at the left side or the right side, or whatever, somewhere. Okay, you know, this algorithm is very good. And then no matter where you choose, usually will not affect the answer. Okay, will not affect the answer, but of course it will affect the efficiency of your algorithm, which means if you choose different, I guess probably you need more steps, okay, to converge. And this is the first comment. And then we have the second comment, when to stop iteration. Okay, and then we do this whenever you see as converges, okay, and then stop. What does the convergence mean? Usually we do algorithm is based on the desired accuracy. Like if the question asks you to round it to 6 decimal places, if you see all the 6 or the 7th decimal digits are the same, which means converge within the desired accuracy, so we stop. Okay, these are the two comments. Now let's practice only one question, okay, to see how to use the Newton's method. Here is the question that we have two parts. The first part that asks us to explain how we know that the given equation, this one, must have a root in the given interval 2 to 3. The second part, if we know there is a root and how to approximate, we will use Newton's method. The accuracy they ask is 6 decimal places. Now, let's go to the first part. The how to prove, okay, it's how to show why there is a root between 2 and 3. Do you remember we learned before? We call the intermediate value, right? Theorem. We learned that theorem before. All we need is look at the value of the function at 2 and at 3, right? If they have a different sign or the opposite sign, and then we can show, okay, we can prove there's a root. Let me going to do that. Okay, so here the first part, let me put here. So of course we need to set up a function, right? So otherwise, so we cannot. So let me this function. Let this f is the half, okay, the left side, which is 3x4 minus ax 3 to the power plus 2. This is a function. Now we need to verify the intermediate value condition, right? So first, is this a continuous function? Yes, continuous on 2 to 3 because there's a polynomial, no problem. The second, look at the value. F at 2. We're going to verify is negative 14. See, the sign is negative. The same the right side. If we evaluate it, that's 29, which is a positive. So that's good, see. And the left is negative, the right side is positive. Of course, in the middle we have a 0. Therefore, now we have the conclusion by, remember the name, we call the intermediate value theorem. So by this theorem, what do we have? And this function fx equals 0, which is this is equation, right? Has at least one root in 2 to 3. We did this before. So now, what do? We are going to use Newton's method to approximate this root between 2 and 3. Let me see. Okay, so first, let me copy Newton's method. The second step is the major one. So let me put here. It's a Newton's method, right? we are going to use Newton's method to do approximation. Let me copy the formula, which is xn plus 1 equals, to remember this, xn minus f at xn over f prime at xn, right? N is from 0, 1, 2, and goes to infinity. All we need here is f, the function f, and the function derivative. So what is f? Fx, let me going to find it, f, the function. See, it's this polynomial. Let me copy the formula here, which is 3x4 minus a x the third power plus 2. Okay, good. We have the function. Now, we're going to find the derivative. The derivative, of course, is easy. There's 12x raised to the third power minus 24x raised to the second power, right? And we follow this formula to iterative algorithm, right? So the first, we need to start from x equals 0, x0. Okay, so let me choose where to start. Choose x0 equals, okay, see, we need to find a root between 2 and 3, so we can do this. Probably you can choose 2 as the starting point, or you can choose 3 as the starting point. If someone like, you can just choose the middle, 2.5, or whatever, which number between 2 and 3. Let me choose 3. That's okay, the right side. Let me choose 3. Okay, so all set up. And then we need to find x1, right? What is x1? I will write the x1, the formula. Can you see? In this formula, we set up n equals 0. Therefore, x1 equals x0 minus whatever, right? So it's this. Minus fraction f at x0. F prime at x0. Okay. Don't mix this. This is not a prime. Okay, it's there. Okay, if we plug x0 is 3, we choose minus f at 3, right? F prime at 3. Because both functions we already defined, therefore easy to evaluate. After evaluate, what do I get? I wrote the results directly. Is 2.7314 A1481. Okay. Let me see. It's very long. And this is the one I get from the calculator. So now what do? We cannot stop. Now it's only one number. So I will continue to find x2. The same. Can you see? I will going to find x2. What the formula? This time we should use the previous results, which is x1, right? We know x1. At least we know the approximation. So x1 minus what? F at x1 divided by f prime at x1. Okay, so x1 is a little bit longer, so I did not put. Now we can evaluate, right? Definitely. Let me directly give you the answer I get from the calculator, which is 2.6404 35,397. I wrote it as long as possible. Okay, if you do these questions, I suggest you write this as long as possible. Why? Because see, in this step we need the results from the previous step. Okay, if you write it as long as possible, we give you accurate. Okay, so much better results. The same, right? We get x2. Now we have to move on again. So what is x3? So x3 is this. should be use x2, right? We already have x2. So minus f at x2, f prime at x2. Okay, so let me get the results. 2.6. See, looks much better. See, this time much closer, right? This we call the kind of converge. 3, 0, 1, 4, 55, 27. Now the answer, this x2 and x3 are much closer, right? But not closer enough to stop the iteration. So let's going to find x4 again. So x4, of course, is the same. We're going to is this. We use x3 minus f at x3 over f prime at x3. And I already get the approximation results, which is 2.6, 3002, 0273. Now see, what do we have? We have x4 and x3 much closer, right? But we cannot stop because what? The accuracy, we need to go to 6 decimal places. See, these 6 decimal places are totally different from that 6 decimal places. Therefore, we need to move on. Okay, and then let's going to find x5. So now, what is x5? x5 should be use x4 minus f prime x4 over f prime at x4. Okay, so you're going to evaluate. See, what is the results I get from the calculator is 2.6, 300, 20255. Now we stop. Why? Imagine. So we look at this 2.6300020. Okay, or you say it's 2.02, which means the first 7 decimal places, and is exactly the same with this. Can we find they are exactly the same, which means what? If they ask you the accuracy only to 6 decimal, this time we definitely can stop. Okay, because what? Because the 7th decimal are the same, so the 6th or the 7th decimal are totally the same. Okay, we don't need to talk about the rounding. So good. What do we have now? Newton's method give us an answer. So the answer should be 2.630020. Okay, we don't need to look at the 2 another, and because there is a 6 decimal, right? So here is the answer. Now I have one comment for you. If we do calculation, we do not exactly type all these numbers because it's so long. And then now I will going to use a calculator how to simplify this calculation. Here is my calculator. So I will going to define this function in the calculator and then use that function to find the answer. Very, very easy. Okay, so I'm going to this, we define the function, which is y equals x minus fx over f prime at x, which is x minus parenthesis f is this function, right? So that's 3 times x raised to the 4th power minus a times x raised to the 3rd power plus 2 parenthesis divided by denominator parenthesis 12 times x raised to the 3rd power minus 24 times x raised to the 2nd power. Let me make sure. X minus f x, right, over f prime x. Good. Now we have a function. Okay, so how to do this first step, which is the function at 3, right? Let me go into find the variance. Go into y far as the function. Okay, y1 is the one we just deposit, right? And okay, the first x1 is this is the function at x0 is 3 and the parentheses, see, and this d1 I already wrote here. Okay, so wrote as long as possible. And then how do you find the x2? You know, here is x2. Let me get to here a little bit. See, we're going to x2. Okay, so x2 should be the function what we defined at x1, right? Okay, so the same. We're going to find the y1 again. See, parentheses add this previous answer. The previous answer, which is, can you see, second negative, which is the previous answer. Second negative parentheses. So we will find that now is x2, right? Can you see? Is this the same as I wrote here? Of course, they're the same, right? Now, do the same way. We're going to use a y1 at the previous answer, which is the same entry, to find the x3. Now is second, see, the previous entry is a second enter. This is the previous entry, and then enter again. So now x1, x0, this x3. Is x3 the same? Yes. The same going to second entry, which is x4. Can you see? This is x4, right? One more, can we second entry, and this is x5. Okay, so that's whatever I get from here from the calculator. Super easy to get in the calculator. That's all. Thank you. I hope you enjoy learning on this topic. If you have any questions, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. We are going to deal with the antiderivative, which is the inverse process of differentiation. Hope to see you there. Thank you. Have a nice day. Bye.